Alright, I'll get started then. So this is Functional Programming for All. I'm Zachary McCoy. So just a little bit about me. I've been doing Scala for about 4 years now. I'm from the US in Iowa. If after the talk you want to talk to me at all, my Twitter or my email is usually the best way to get a hold of me. So to really do functional programming, we have to understand what it is, right? So at its basic core, it's just programming the functions. So if functions are actually our main abstraction, then all we're doing is composing functions over and over again. So that also means that our functions are first-class values. And what that means is that our functions also return functions and can take in functions. So in functional programming also, we have controlled side effects. We don't have them littered throughout our code base. They're in one area usually, and that return type is unit, or might be task if you're using ScalaZ. So functional programming really just restricts how we actually write our programs, but not what we can actually express with them, and that's really important. So what we really want is a pure functional core, so a lot of little functions that are purely functional. We'll talk about what that is in a second. And then a layer on the outside that interprets those and does our side effects for us. So a side effect, though, what is it exactly? How do we describe that? Our programs are essentially useless without them. We don't have anything that actually happens, but we don't want them littered throughout our code base either. So a side effect is actually anything that happens that's in addition to returning a value out of a function. Whether that's a print line that you put out there, a log, or sending an email, or anything. So functional programming is actually about evaluating expressions. It's not about mutating data of any sort in vars. It's not about pulling from out of scope. Imperative is actually all about composing statements. So we want to mutate this value that all these functions are pulling in. So we really need to get down to also like what is a function, mathematically speaking. So it's an expression that's involving one or more variables. Those variables are the parameters that you're passing in. And with a function, there is a domain and a codomain. The domain is all the input values, and the codomain is the return values. So really we're talking about a unique mapping from the domain D to CD, which is our codomain. And with functions, we're always producing something new. So everything's immutable. So really, what's a pure function then? It's just a function in math, that's all it is. So it's the exact same thing as what I was talking about before. So they don't have any observable side effects at all. And once again, a side effect is just anything that's not returning a result, whether that's mutation or I/O. And it also, another important thing about this is it only depends on the arguments or subset of them that are passed in. In a lot of our functions, we have this implicit argument list, whether that's a database connection or something else that's outside of the scope. All you need to do is pass that in. So some examples of pure functions that are probably in your code base. It might be hashing or arithmetic. Anything like that is actually a pure function. So why do we care about pure functions compared to anything else? So for one big one is all the side effects that are in your code base cause all the order of evaluation to actually matter. If we're mutating a variable, and that's our side effect, then the order now actually matters to whether I called F1 or F2, if they both actually rely on that variable. So we only actually have to use local reasoning also. So local reasoning just means that I have to care what's in the scope. what's in scope of my function. I don't have to care about the implicit argument list of other scope, whether it's that database connection and I don't have a thread to actually use it, or if someone's changed a var on me. So with purity then, we actually get composition and reusability of our functions if we break them down enough. So what we really want to do is we want to separate the computation over the input from actually how to obtain it. So if we're pulling from a DB, pass that value in. Don't have it happen inside of the function. And what this actually gets us then is purity actually guarantees us referential transparency. So referential transparency is a big word for something that's actually really, really simple. All it means is that an expression can actually be replaced by the value that it's going to be evaluated to without changing the meaning of that program. So that function, though, can only be actually referentially transparent if the inputs are also referentially transparent. And referential transparency actually enables equational reasoning then. And equational reasoning just means that we're able to separate equals to equals. We can replace a function call's value of what it's actually going to evaluate to with the actual function call area. So we have this function here, greater than 5. Takes in an int and returns an option of int. And then we have the body also that just says if I is greater than 5, return some, else none. We're replacing that body of that function in create message 2 and putting it where that call is. And eventually actually evaluating it down to none. So substituting that body, or that function call, to none, we're able to do that because of referential transparency. If that possibly changed a var, or if it maybe sent a message to an actor, the effect of the program would be different. So to formalize this, any expression E is actually said to be referentially transparent if E can be replaced with its value without changing the actual behavior of the program. So what this really means for us is that we have the same effect and output in the end of the actual program. So some examples of math, some examples of referential transparency then. Mathematics. You're able to replace the expression 2 times 2 by 4. Other ways we might be doing this in our code base might be returning our errors as values. So instead of throwing an exception that says we're out of memory, we have some value that we actually pass out and then are able to compute on later. So how does this all actually tie together then? How do pure functions and referential transparency tie? So with pure functions, we actually gain referential transparency. And through referential transparency, we can use the substitution model and equational reasoning. What this means for us then is that our code's easily testable and reasonable. We can reason about our code base much easier now. So our type system, though, doesn't actually allow us completely to say that we have a pure function. We still have to actually work for this. So in some languages like Haskell, we actually might have I/O. But here, we actually have to just annotate around, essentially. What that means for us, though, is we actually have to limit what tools we use. We need to not be using vars that are global. We need to not be pulling from out of our scope, so that implicit argument list, once again. And we shouldn't be throwing exceptions. We should be returning errors as values. So with any function that we have, whether it's computing and print lining or anything else, we have some function of type A to C. And we can actually split that into 2 functions. There's a function A to B, where B is actually a description of some result, or something to do. It represents our side effect without actually doing the side effect right now. And then we have another function, B to C, which is actually an interpreter over that, over all those descriptions, that'll do the side effect for us. So now we have a pure function and an impure function. One's completely testable, and we know that all of our side effects are in one other area. So let's go through a small example then. We have some case class person, which has a name and an age. And then we also have two people. We have John and Jack. One's age 30, one's 100. So we have this function calculate oldest. It's pulling those two people from out of scope, checking their age, and print lining whether they're who's the oldest or if they're actually the same age. So this function returns unit, it's side effecting, and it's not really testable. So this is that same function, but now we're actually passing in our two variables, P1 and P2. We're no longer pulling those from out of scope. We still return unit though, so this actually can be still made better. So now calculate oldest actually returns that person. Depending on if they're actually equal or not, it returns some or none. So this function is actually pure now. It's referentially transparent. We are able to replace the call to that function with the actual value that it's going to evaluate to. And then we have this function, result. This takes our option of person, and then side effects. It returns unit. This actually can still be made better. We're actually able to still split this out a little bit more and have two pure functions over our side effect. So what we really want to do is actually write a description of the program and then interpret over it. So the end result for us is actually, we have one pure function, calculate oldest, which takes in the two people and returns an option of person. We have result, which takes that option of person and returns a string that we actually want to side effect with. And eventually, we actually want to compose those two functions and print line the actual result. So we pulled out all of our pure functions, and now we have one side effecting one. Both functions on top are actually completely testable and easily reasoned about. We actually want to strive for as many pure functions as possible and have our interpreter over the description for side effects. So try to imagine how this would be useful in your code base. Yes, your code's much more complicated, most likely, but this is doable anywhere. So FP is actually all about these concepts. It's still about referential transparency and purity. It's just all these libraries like Scala, Z, and Cats just use these concepts. That's all.
質問ある方いらっしゃいますか？もうよろしいですかね。じゃあ、Thank you.
ありがとうございます。スカラはファンクショナルプログラミングランゲージですけども、オブジェクトオリエンティッドプログラミングランゲージでもあります。FP をやるにあたって OO とどういうふうに共存させたらいいというとこ に何か知見はあるでしょうか。オブジェクトオリエンテッドプログラミング、ファンクショナルプログラミングの TXT。スカライズ、
So, I'd actually say you can write pure functions anywhere, right? So, personally, at JHA and Bano, we strive to go completely functional as much as possible, within reason also. Anything that you can do with OO can be done with function programming, right? So, I think it's really where you want to draw the line for which to use. Once again, like it doesn't actually restrict what you can express, but it just restricts how you write them.